The science of harmonics in music. What is music? Music is energy in the form of a wave or a vibration that travels through matter and eventually reaches your ear and causes it to vibrate at a certain frequency. There are three fundamental properties of these waves or vibrations, and they are the amplitude or intensity, the frequency at which it vibrates, and the tone or timbre. Graphing the intensity versus time, you can see that it is a periodic function. This distance here is one wavelength, or 2 pi radians, where the frequency is the amount of radians per second. Let's draw another wave. It's very pretty. Now, let's erase that and draw an ugly one. The interesting thing is that both of these have the exact same frequency. This can be seen by overlaying the two waves. Their fundamental frequency is the same, but what causes them to be different are the differences in harmonics. But what are harmonics? Okay, so let's start out by drawing a fundamental frequency with an amplitude and it repeats periodically over a certain amount of time. And we'll call this the n=1 mode. A normal mode meaning an orthogonal mode, where each one of these wavelengths I'm going to draw are orthogonal to the other, and that means that they are independent of each other. Mathematically, this is equivalent to the orthogonality of sines and cosines. Now I've just finished drawing the n=2 mode, or the second harmonic, which has twice the frequency of the first. For acoustic normal modes, this is referred to as an octave. So what's interesting is that the harmonics in music are actually very long wavelength phonons. Now let me just draw in the third harmonic. The third harmonic completes 3 whole wavelengths by the time the first harmonic has completed 1. Duh. Notice how the first and second harmonic meet up at the halfway mark on the x-axis. However, the third harmonic does not meet up at all except for on the 2 endpoints. So this leads into our musical system that most of the world uses. So we're going to talk about octave equivalence, or the fact that notes with 2 times the frequency are considered the same note. But why? The answer is logs. For some reason, we seem to perceive music in log base 2. This is known as the miracle of octave equivalence. So say we have a frequency vibrating at 440 Hz, or an A. 880 Hz is also an A, as is 760, and finally, 3520 is also an A.
Alright, so now that we know about harmonics, let's find them on the piano. So let's say that this C is our fundamental frequency, or the first harmonic. Here's the second, here's the third, a G, and here's the fourth, another C. This makes sense, because 1 times 2 times 2 is 4, and so any multiple of the fundamental frequency times 2 to a power is equal to the same note. Those are all the same note. Something interesting is that nothing is added to the chord through these harmonics, nothing new at least, unless they are new prime harmonics. For example, 3 and 5, we can add them to the first, second, and fourth harmonics, and you'll get this. A major chord. Not only do the harmonics sound good together, but each note has its own harmonics that it fundamentally creates. So take this C again. The sound you're hearing is not just the frequency that corresponds to that C. It also has all of the above harmonics. So to prove that this C contains all of these harmonics, I'm going to try to bring out one, the third. This is the third harmonic of this note. So what I'm going to do is I'm going to push this down, therefore allowing it to not be damped by the piano. And I'm going to play this note. And if I'm correct, then the harmonics created by this note will vibrate at the correct frequency to cause the spring inside the piano for this G to vibrate as well. So after I stop playing this, you'll hear this G continue to ring. Let's see if it works. You hear that? Listen for that. So there you go. So I'm going to do some overtones, And overtones are interesting because they are harmonics, and the way they work is the human voice creates these overtones, but depending on how my mouth and throat and tongue move, they create different sized cavities, and these cavities create resonances for these different harmonics depending on how I move. So I can somewhat control which harmonics I want to bring out. And so let's go.